Hello everyone.
Hi, Anurag.
Hi. Can everyone hear me? See my screen?
Yes.
Okay. Thank you. So, welcome to Lab 4. I'm here alongside my fellow TAs Malia, Kusi, and Olivia. Uh, Let me just start with the presentation. Um, so, the goal today is that Malia and Kusi are going to give a brief overview on how to compute the derivatives and give you a rough idea of the Autograd engine that you would use for your homework on Autograd bonus part. And then we'd also delve a little bit into the details of it through some example. There is the Piazza post with Lab 4. The link for the student notebook should be available to everyone. Please let me know if it's not. The students here in the class confirm that they have access to the student notebook for Lab 4. The post has been made on Piazza. Let me know if you guys don't have access to it. It is. Sorry. Okay, we're gonna get started with the presentation. Let me just do this for now. Malia and Kusi, let me know when you want to start the presentation.
Yeah, I think we can start.
Okay.
So,
Okay. The floor is yours.
okay, so hello everyone. Welcome to this lab 4 of computing derivatives and Autograd. Today we'll be learning about what are how to compute derivatives and how and why Autograd is important for training neural networks. By the way, I am Khushi, and with me we have TA Anurag as well as Malia. So now the first very important question, like what is derivative? Although we all know about this, but just knowing it in brief, derivatives are something that tells us a rate of change. Now suppose your position is changing with time, so here the time is input and your change in position is the output. So its derivative are simply just with a changed input, how does the output changes. So now we do have next question, that why do we need to compute derivatives. Firstly, derivatives are a very powerful tool, like they gives us insight and they unlock insights of how things work, like how things move, everything. But apart from that, why do we need to compute derivatives when it comes for neural networking. So now we'll take a very small example to understand this. Suppose you are on a hilltop and you want to go to the lowest point. Now you know the direction that you have to move is downward. So derivative also act the same way. Like they tell the model which way to move just to have a reduced and minimized loss function. So when we are training a neural network, we want to adjust the parameters so that the loss function just get smaller. And to do that, we need to know that if we are changing the parameters, if we are just tweaking the parameters a little bit, how will the loss change, like will the loss function increase or will it decrease. So it somewhere brings a sensitivity, and that sensitivity is exactly what derivative gives us. So now we do have a problem, like model network have millions of parameters, or even we can say that they have billions of parameters, and calculating derivatives for them by hand is almost near to impossible. So for that we definitely need to find a way by which we can automatically calculate them. um, Moving further, there's one bonus homework for you that we have for autograde 1 that has been released on January 15th, so you all can complete that and gain bonus points. Now we'll look for some methods of solving derivatives. Now the first very common method is hand coding derivatives. Now in this method we use simple calculus rules to calculate derivatives, like chain rules and all. So here we are solving derivatives manually. It do have few pros, like if it is well implemented, it could be fast and exact, but since it is done manually and by hands, it is more error prone. And in terms of generalizability, it is almost near to wasteful, because if we are just changing a parameters a little bit, at that point we have to redo the calculations from scratch, and also it is time consuming. Now we do have a second method, that is numerical differentiation. In this, what actually happens is that we give computer a value, and we just nudge that value, and we see if the output that we are getting is equal to our estimated output or not. So basically we insert a epsilon value into that derivative, and choosing the epsilon value is quite tricky, because the epsilon should not be very large, or it should not be very small, because if it is large, then the output that we'll be getting will be far from our expected output, and if the epsilon value is small, then there will be number precision. Pros of having numerical differentiation is that it is kind of easier to code, because here we are just approximating and guessing values. But it has a cons, like over time it can accumulate a lot of error, because in numerical differentiation what we are actually doing is that, like, we are just estimating things, like we are not computing them, we are not calculating them. Instead we are just estimating values. Now both these methods sounds quite painful, so for that we have another method, that is auto differentiation. Okay, so auto differentiation is like when the computer itself is solving the problems on its own, and it breaks the problem into small portions, like there are small parts over which the problem is broke down, and those smaller blocks are called as primitive operation. So now we'll talk a little about primitive operations. So primitive operations are nothing but just the smallest building blocks of computation in automatic differentiation. For example, like we have addition operation, subtraction, multiplication, division. Apart from that, we have some nonlinear operations such as exponential, log, sine, cos, and there are few activation functions such as ReLU, leaky ReLU, etc. And these functions are consisting of many primitive operations, and Autograd tracks these operations to build a computation graph. Now we will understand it with how it works. So basically we start with an input, like we give any expression, any derivation to the computer, that then it breaks it in small parts, and then PyTorch breaks everything, and then firstly it breaks everything, then it connects everything to give us a computational graph and give us the expected output. Now pros of auto differentiation are very the backward function is very automatic in this, if computation graph is correctly formed, and the calculations are exact. But while implementing the forward functions, we have to be very careful, like if we are not making the function in a right way, then at that time the whole output that we'll be getting will be wrong. Now we'll understand this with an example. So here we have a expression, that is f equals to b times a plus b. Now our goal here is to figure out, if we tweak the values of a and b, how it will affect f. So now for the first case, we have gradient of f with respect to gradient of b. So here, keeping a constant, we have this output, that is b plus a plus b, and on solving this we'll get 2 times b plus a. And here for the second case, we have gradient of f with respect to gradient of a. Here we have kept b constant, and on solving this we get b. So now we'll make a computational graph for this. Now, understanding why we need to create a computational graph, like creating graphs is much easier because it makes us very familiar with the expression. It makes us easy to understand what the expression is telling us. So here we do have also in a computational graph, the nodes represents the operations and the inputs, whereas the edges represents the path. So here we do have this expression, that is f equals to b times a plus b, and we have this graph. So in this graph we have two input nodes such as a and b. Then we have a primitive operation, that is plus. Now since we can see in the expression that a plus b together forms like they both combine, so we have generalized it and named it as c. Then this c is multiplied with f, and also this b input is also multiplied with f to give us the expression. Now we'll analyze how this work. So next slide, please. Yeah. Oh, just can you get a please previous slide?
Okay.
13th, yeah. So here we do have, like, we'll start with traversing in the backwards. So since f is the final node, we will start from f. Now gradient of f with respect to gradient f will be 1, because gradient of any number with itself is 1. So since we have calculated for 1, now for every node we will use a chain rule to calculate its gradient. So since we have calculated for f, now we'll move to next further steps. Now we will go in reverse topological order. Now we have calculated for f. Now we'll first go to c, then b, then a. Now for c, we have this function like f equals to b times c. So for here, keeping a gradient of f with respect to gradient of c, on solving this, we get 1 times b. For b, we have gradient of f with respect to gradient of b, and solving this, we get 1 times c. Now, okay. So now since we can see that on C, there are like two input that are coming on C. Like one is from F itself and other is from B. So we will solve for A also. Now when we talk about A, so we will do gradient of F with respect to gradient of A. That will be 1 times B times 1. That will be eventually 1. And next please. So similarly, here we can see, just since C has two operations, that one is from F and other one is from B. So we have this calculation at the last where we are adding the derivative of B as well as gradient of C. So in output, we get 1 times C plus 1 times B. Now we will get this final solution as this one. Now Maliha will take over and she will take you through the next slides. Okay, so thank you, and over to Maliha.
Okay, so now let's understand how the autograde frameworks actually works internally. So autograde is based on something called a computation graph. So each value represent a node, and each operation like plus, multiplication, etc. becomes an edge connecting node. So here we can see a node A and B, and then plus operation which produces C, and then it gives a multiplication. It gives multiplication and gives the final output as F. So internally, the system does not just store the number, but it also stores the value and how it was computed and who its parent node are. So during back propagation, gradient flow backward through this graph using the chain rule, and that's how the PyTorch calculates gradient automatically without us writing the formulas. Um, now let's see how single node is implemented in a code. Here we have a class called node. Inside this constructor, we have self data, which stores the actual numerical value of numpy array. And then we have a self grade, in which it stores the gradient and is initialized to 0 using this np.0 function. You will be using this in the homework 1 autograd. And then we have self.parent, which stores the parent node in the computation graph. Now, why do we store parents? Because during backpropagation we must know which node contributed to the current node so that gradient can be passed correctly. So every node knows its value, its gradient, and where it came from.
Okay. So this is the time for the first checkpoint for you. Please head to Piazza. Open the notebook. I would recommend to open it in this Google Colab. In any browser. It's easier that way. Just go. Just do upload. Go wherever the downloaded file is. For me, it's over here. And then, so yeah, based on the theoretical framework that has been provided by Malia and Kusi, I want you guys to go through the cell 1 to define the class node. We'll have 2 minutes for it. I'll time it, and then we'll also walk through why the answer is that. In the meantime, if anyone has a question, please let us know. Okay. Let's just walk through the solution. Did you guys manage to get something done? A little bit? Okay. Nice. All right. So let's just walk through the solution. Malia already gave you a brief overview of what these things are. So as he mentioned, we need to have an attribute for the node class associated with data. So we just initialize it as an array using numpy.array. Then we also want to keep track of the gradients, right, with every node in the computational graph. So we just start with 0 using numpy.zeros like, which would have the same dimensions as data. And then we would keep track of the set of parents because we want to go back during the backflow. We also have the label, but you can just skip it for now. Any question? Over Zoom, if I'm missing my fellow TAs, please let me know. And yeah, you guys are good with the explanation? Okay. Cool. All right then, we can continue, I guess. Okay, Malia, I see your second.
Okay. Okay. So now we move to implementing the primitives. So as I already said, Autograd works by building a computation graph step by step. To support this, we must define primitive operations like addition, multiplication, matrix multiplication, subtraction, logarithmic, exponential division, etc. Here, each primitive must create a new output node, store the parent node, and define a backward function that updates the gradient. So once primitive are ready, any complex function you will give, it can be built using them. Now, let's start with the simplest primitive, that is addition. Suppose we have an expression which c equals to a plus b. Here, now the derivative of c with respect to a and with respect to b is equal to 1. So during back propagation, the gradient coming into the node c is passed equally to both A and B. So graphically you can see A and B connect to the plus node, producing C. And this is very simple because addition does not change the gradient magnitude. As you can see here, the gradient of C with respect to A and B is equal, so they don't change. Now we will be moving to how now let's understand how the addition primitive is implemented logically. So here we have to first create a new output node, and then we have to add the data of the input node. Then we have to track, so graph should be maintained, and we have to define a backward function. In this backward function, we have a gradient of A which increases by the output gradient, and we also have a gradient of B which also increases by the output gradient. So both input receives the same gradient over here. Now next we have, now this slide shows the actual code for addition. Here you can see a new node is created using the summed data. Here the parent node are stored, and the backward function updates gradient for both input nodes, and the backward function is attached to the output node as well. So whenever backward is called, this logic execute automatically. Now we have, now let's move to the next slide, please. Now let's move to the multiplication. Here suppose we have one expression C equals A dot B. Here derivative of C with respect to A is equals to B, but in addition we have seen it's equals to 1, and derivative of C with respect to B is actually A, but in addition we have seen it as 1. So here the gradient propagation depends on the opposite variable, but in addition the gradient propagation depends, like they are independent and they are equal to each other. So if A is large, then gradient of B increases more, and if B is large, then gradient of A increases more. So you can see the diagram how gradient flow differently compared to the addition. In this multiplication primitive, we firstly store the data values, then we store the parent nodes, and then we define the backward function. In backward function, in backward function, they are like dependent on each other. The derivative of C with respect to A is depend on like B, and with respect to B, it's depend on A. So gradient are scaled based on the other input. So this also correct gradient propagation in deep network. Uh, okay, so now let's look to the code of multiplication primitive. Here we have a function called mul node, in which we have this creates a new node called out. Its data is simply the multiplication of two input values. We also have A node and B node as its parent, so the computation graph is maintained. And now comes the important part, that is backward function. Inside this mul backward, we have this A node grade, this code, and B node grade, this code. This follows the calculus rule. If C equals to A dot B, then derivative of A and derivative of B will be B and A respectively. So during back propagation, gradient flowing into the C is multiplied by B to update gradient of A. So gradient flowing in C is multiplied by A to update the gradient of B. So finally we attach this backward function to the output node, so that when backward is called, this logic executes automatically. This small piece of code is shows how deep learning libraries compute gradient for multiplications internally. Now we move to the scalar multiplication to matrix multiplication. Here we have C equals A at the rate B. Here this at the rate symbol is used, means a matrix multiplication. Here gradient rules become slightly more complex than the previous one, because here the derivative of C with respect to A is gradient C dot B transpose. Why transpose? Anyone, if they can answer? Okay, so transpose is used because matrix dimension must align properly for the multiplication during gradient calculation. So here we use transpose. Now here are some notes written in this slide, like we use this at the rate operator for matrix multiplication, and for dot product we use np dot dot. So this is very important in neural network because weight matrices are multiplied with input matrices, and back propagation requires correct matrix gradient. So auto differentiation must support matrix multiplication efficiently and accurately. So now let's look at the code implementation of matrix multiplication. Now we again create a out node over here. Then we define a backward function. For gradient of a, we have a node dot grade, and we have used np dot dot function over here. So this matches the formula which we have seen in the previous slide. Derivative of c with respect to a equals gradient c dot b transpose. So this is the exact formula, and similarly we have gradient of b, in which it is also matches the formula we have seen in the previous slide. So mathematically and programmatically everything matches over here. So this shows that how matrix calculus is handled inside the auto differentiation engine, like PyTorch. So now we move to the most important part, that is the backward method. So let's take an example. F equals b into a plus b. This create a computation graph with nodes a, b, c, and f. Here we have the edge connecting node of a and b is c, which is a plus operation between a and b, and then we have edge connecting node f of c and b, which defines the multiplication operation over here. Initially we have the backward list is empty, and there is no parent and no current node, so we haven't started the back propagation yet. So now, yes, this slide will now the backward begins from the final output node f. Here we add the add f into the backward list. Then the backward list become contains this f, and we have the parents of f over here are c and b. So we mark node as f. At this point we know that the gradient must flow first from f to its parent c and b. Now next we have to process this c. Now the backward list become f and c, and parents of c are a and b. So we schedule both a and b for later processing, and this ensures the gradient should propagate correctly through all the dependencies. Now we have to process the node b. Now the backward list become FCB. Now you will be thinking why we have not processed A and why we have processed B, because C consists of A and B as a parent node, but we can see that B was there in the queue first, so we have to process this B first. So node B has no parent further, so it does not expand the graph anymore. So this shows how traversal continues backward. Now finally we have node A to be processed. So backward list become FCBA, and now all nodes included in the backward order. After building this list, we iterate through it and call each node backward function. This ensures this the correct order, then no missing gradient over here, no duplicate processing. This algorithm guarantees the accurate gradient computation. So now as we move further, okay, so now we have finished the building the backward list. As you can see, we have this backward list consists of FCBA. Anurag, the previous slide, please. Okay, so this means that the node are ordered exactly in the sequence we need to process this gradient. So why this is important? Because gradient must flow from the output towards the input. If we process nodes in the wrong order, then some gradient will be missing, or there may be any duplicate gradient also. So now we simply iterate through this one by one. Then we first process B, and then we process C, then B, and then A. So this is exactly how real deep learning libraries work. They create backward execution order and execute gradient function automatically. Now, this slide shows the pseudocode of backward method. Let's go through this example by step by step. So we initialize the gradient of the final node of an array. Then why? Because del f by del f is equals to 1. Now we have to initialize the backward list as an empty list. Then we will recursively visit each node. If the node is already in the list, we skip it to avoid the duplication. Otherwise, we add it. Then we recursively visit all parent node. This builds the correct backward traversal order. Now we iterate through all nodes in backward list. If the node has parents, we call it backward function. And this trigger gradient propagation throughout the graph. So the entire back propagation algorithm is only a few logical steps, but it is extremely powerful. Now, moving forward, we will be seeing the code implementation of this backward method. Here, first we have now inside the node class, we define the backward function. Here we have first initialize the backward list as an empty list. Then we initialize the gradient of the output node to once, and then we define the recursive function that is built backward list. Now this function add node to the list, and if not already added, and recursively explores the parent node. So this creates the backward traversal order. Now we have this loop for loop which executes the backward function for each node. So once we call this output dot backward, the entire gradient computation continues automatically for all connected nodes, and this is exactly what happens internally when we use PyTorch and backward function. So after this, Anurag will take over.
Okay. Thank you, Malia, for the explanation. Now let's try to make this simple computational graph involving the same set of operations based on which we have defined all of these functions and classes until now. All right, so we have node A, node B. We're going to set them to 7 and 0 for now, and then we want to call the backward function on them. So the basic auto differentiation engine that we have built based on this specific example, let's see how to use it, right? So we're going to initialize A and B to node 7 and node 8. Remember, node again is a class with data, parents, and gradients as attributes. Here we haven't set parents and gradients until now. That would be accumulated as we proceed forward. Then we have our node C, where we're supposed to put the value after adding node A and B. And we have node F, where we're supposed to put the value after multiplying C with B, right? And as Malia mentioned, we will start by initializing an array where all the values are ones. So that's what we're doing here. And then we would call this global backward function or class, as you might want to call it. That would automatically trigger the backward function associated with each of the nodes. So if you notice, this is the global backward function. Then we have our backward function associated with each of these, with matmul, sorry, matmul is not relevant for this example, but multiplying the nodes. You have the mul backward. For adding the nodes, you have the add backward, right? So, yeah, I was here, yeah. And then we're just gonna print what we can simply print what the gradients associated with node A, B, C, and F are by simply printing the node. I mean, the gradient would be inside the attribute of the node, but that's for the sake of brevity. So I'm gonna tell you something right now that if you understood it, you understood most of the theory that we're trying to cover today. So for the larger operations, right, you always want to call your primitives. You always want to define things as nodes that you have already instantiated or defined. And all you need to do is call the backward function at the end, and the derivatives would be computed for you, right? If you manually create new nodes, and they must not rely on the input data that you have on your existing computational graph. If you want to use it from the data directly from your computational graph, you must use the primitives that you have defined while building the computational graph in the first place. If you don't do that, it might break, right? I'll try to explain that with a small example. I'll try to write that on board. Let me know if it is not visible for you guys. Matt? Do you think it will be possible to... Yeah. Put that in there? Okay, I would try to write it on both. So we have oh my bad. I assume this is not. Should be fine, right? Okay. Is the example visible to everyone? Okay. Right. So the first example, where let's say we had the node A, right, in our example, and we just want our other node 2A that stores twice the amount of every element that we had in the initial array or the node. So the natural thing that people might do is just say, oh, instantiate new node as a dot data times 2, right? This would be wrong. It would break the computational graph. Instead, what you would want to do is you initialize no node with data 2, right? And then you just perform mul node primitive on your first array A with this new node that you have already instantiated. What it would do is automatically trigger the backward function for this new node as well, and put the gradient associated within the right reverse topological order in the computational graph. The reason why this is safe is because like node 2 is something whose gradient would essentially be 0 because it's a scalar, right? And we don't really care about it, as opposed to the first example, where we definitely care about the gradient associated with this for our computational graph. Does this make things clear for you? Okay, cool. Any questions in Zoom? Again, my fellow TAs, please let me know if you see something that I missed. Okay. Uh, Matt? Matt? Yeah, we can just. Okay. Now, this is another checkpoint. I recommend everyone to go to the student notebook and start working on add node, mul node, mat mul. We'll have like 5 minutes for add node and mul node, and then 2 more for mat mul. So I'll keep track of it.
क्या
Yeah, what was it again? Okay. 7 minutes has passed. Let's just try to walk through the solution, right? You've already seen the solution for the most part, but we'd go through it once again so that everyone's on the same page. So if you remember, we have node A, node B. We want to add them and then put it to node C, right? Our C here would be output node out. We're going to instantiate the node class there. The data for this class would be the addition of the data from node A and node B. That's what we're doing over here, right? And if you remember, the second parameter was the list of parents, the tuple of parents, which is A node, comma B node. All right. Then we're just gonna call this define this backward function, which would tell us what the derivative of what's the gradient associated with node A and node B is, and we're just gonna add this with the uh, instantiated gradient in the beginning, which if you remember was 0. And one thing that I want you guys to focus on is that we do plus equal to here in both of the cases. Why do we want that, especially for this example, right? If you go back, you have gradients flowing, right? In let's say for node B, right? You have gradients flowing from this direction from F, and then from this direction from C, right? You want to keep track of both of them. So it's just like a clever way of putting things together. We do the same thing for the multiplication. We define our output node. We add the data of node A and node B first of all, and then we just try to put node A and node B as the parents. And as Malia described, we're just going to multiply the data of node B with the gradient of C, and put it with as the gradient of A, and we do the same thing for the gradient associated with node B as well. And in both of these backward functions, we are then going to invoke the dot fn. We'd put the dot fn attribute as the pointer to this specific function and this specific function over here. Does that make sense? Okay. Anyone in Zoom, if you have question, please put it in the chat, or you can just raise your hand or ask as well. Anyways, we're gonna do the same with matrix multiplication as well, right? In Python, you can just use array to define the matrix multiplication, the set of parents node A and node B, and as Molly had discussed, for the gradient of node A, you would want to use np.dot because you are doing dot product of node B's data and the gradient of node C, and same for node B as well. And you would see these transpose in different places just to ensure that the dimension of the product that you're doing is it makes sense. And then you would put this attribute backward function to this specific node output node, and to the pointer of the function that you have just defined over here. Okay. This is the global backward. I didn't give you guys time to do it because we are short on time. But yeah, as Malia mentioned, right, you'd initialize an empty list. You'd have an array of gradient associated with each node. You instantiate it by using ones like. You wanna have a bunch of ones, right? Because you're essentially doing multiplication as you proceed backward, and multiplying something by 1 would make no difference. So this is also another mathematically clever way of doing things. We build our list, right? We append every node over there. We go through the parents, and then we build and we call the build backward list, right, recursively. After that, we iterate through the backward list. We invoke the backward function associated with each of those nodes, then yeah, our entire backward pass is triggered this way. I hope this made sense. Any questions until now? Cool. Anyone in Zoom? Okay. All right. All right. Now we talk a little bit about some of the activation functions, right? You should all be familiar with them by now. Now that you're done with homework one, I assume. So the mathematical expression we all know for soft plus is ln 1 plus e to the power of x, right? So again, the entire throughout the entire lab, we have said that we want to define things with nodes and primitive operations, right? We have the add node primitive define, right? We have x is just an input, right? We can instantiate np.once like for one, and for the easiness, we have already we will provide you with the primitives for log and e to the power of x. You can decide to use it for your assignment as well. Be careful, you might need to tweak a thing or two here, because here we are dealing with nodes and computational graph, whereas for your Autograd homework, you would have a list of operations and you just define a operation class. And then, but conceptually, the ideas are super similar, should be like 60 to 70% similarity, right? Let's look at the code for soft plus. Again, this primitive has been provided to you, x node x, right? We're just defining this term over here. And then we want to, what do you call, have some node associated with one, right? So for that we have np.ones like x dot data. What it does, you'd have an array full of ones whose dimension is same as that of x. Then you'd want to add this one with e to the power of x, right? That's why you call your primitive add node that you have built in this class. And for your output node, you're just going to call the log node primitive, which again, we are going to provide for you. Let's try to talk about leaky ReLU right now. So you guys know the normal ReLU, where you just where the mathematical expression is just max of x, your input value, or 0, right? The problem with ReLU, I'm pretty sure you have heard about it multiple times, but just so that we are on the same page, the problem with ReLU is it can cause vanishing gradients, right? Because imagine all of your values are negative, right? Then your ReLU activated value is going to be 0. So you would lose all the information associated with that particular perceptron. And you don't want to do that. To solve it, people use max ReLU, where they define hyperparameter alpha so that they can keep the neuron kind of active. These values are typically smaller in values. But anyways, so what are we going to do is we will create a node to keep track of these alpha values, right? We should have the similar shape to the input data. And then we would do, we'd keep track of, we'd use two masks, the positive mask and negative mask, where we'd invoke the wave function from the numpy array. This is going to make sense when I explain you the code. I'm also thinking of using an example to explain this. So bear with me, right? So these were the primitives that we were talking about, the exponent node, the log node. And we're also going to provide you with the division that you'd use a little bit. Oh, yeah, okay. So let's say we start with something like this, right? We have an array 2, 3, 5, and -1. First of all, you would want to have an array full of alpha values, right? So what you do, you have your alpha is a scalar. You first of all would use numpy.ones like put your data over there, and then multiply all of those ones with alpha value, which in our case is instantiated to 0.01. And that would give us 0.01, 0.01, 0.01, and 0.01, right? Now, we'd have two of these masks, the positive mask and the negative mask. So what they would do is like, they would only have values in the respective position where it is either positive or negative in the original array, right? So wherever the input data is greater than 0, we'd have 1, otherwise we'd have 0. Wherever the input data is smaller than 0, we'd have 1, otherwise 0, right? So this is just how we have defined things, right? So 2 is greater than or equal to 0, we have 1 here. Minus 3 is not, so we have 0. 5 is, so we have 1. Minus 1 is not, so we have 0. And for the negative mask, we only have 1s in the negative, for the negative values, right? So for minus 3 and minus 1, we have 1 and 1. For non-negative values, we have zeros, right? For 2 and 5, we have zeros. Then what we would do is we would use the mul node primitive that we have already defined to get with the negative mask, right? Because that's where we would need it. We'd only need this operation when it is smaller than or equal to 0. For the positive part, we're just gonna multiply the input with the positive mask node that we have just defined. If you do this, right, alpha mask node is gonna give you 0.0, 0.01, 0.01. For the positive part, you'd be left with 2, 0, 5, and 0. And then for your negative part, you're just going to multiply the input with your alpha mask node. That would result in 0, minus 0.03, 0, minus 0.01. And then you're just going to add them, right? So by having these two separate parts and then adding things pairwise, we would get our final output. Does that make sense? Okay. Any question remotely on Zoom? Do I see something? Okay, cool. Since we don't have any questions, we can talk about 10H activation, right? So we all know the mathematical expression e to the x minus e to the minus x over e to the x plus e to the minus x, right? The most important thing that we want to do is like incrementally build our graph, our computational graph. We don't want to break it at any point in time. So we're gonna instantiate separate node for each of these, right? We'd have separate for e to the x in the numerator and the denominator. We do the same for e to the power of minus x as well, right? And again, the only operations that we have defined until now is add, right? We haven't defined what subtraction does, so we'd see how to work your way around when you have something like that, right? Okay. So first of all, you just have a bunch of ones, negative ones, right? By first of all calling np.ones like on your input data to have an array of ones whose dimension is the same as input x. Then you multiply each of those values, right? Oh, sorry, this is the exact same thing that I asked you not to do a couple of slides later when I wrote things, right? So no, we can afford to do this because we don't really care about the gradient of -1 because it's a scalar, right? So we can do this. Then we have negative x1, right, where we're just gonna multiply this -1 with our existing x, right? So this is gonna give us minus x. Our exponent of x is going to be x node x, right? We already provided you with this primitive. Then you do exponent of negative x, where you just call the exponent primitive with the negative x node. And negative exponent of negative x, x, right? Which is where you just multiply exponent of negative x with the -1. So this is just for the numerator, right? You have e to the x minus e to the minus x, right? So since we haven't defined what the negative operation is, we have to go through all of these steps, right? Um, then you'd have to combine, right, exponent of x1 and the negative exponent of negative of x2. Even though it's an add node, because it consists of a bunch of minus e to the power of minus x, it's essentially the same as doing exponent of x minus exponent of minus x. We do the same for the nodes in the denominator, right? And then we have also given you the division node primitive, so where you just take the numerator and the denominator and then just divide them. So we have separate e to the x for numerator and denominator. Why we want to do that? Because we don't want our computational graph to miscalculate anything, right? We don't want it to be overwritten or get confused of which one is e to the which e to the x are we referring to. Okay. All right. All right. So that's more or less the theory that we wanted to cover. Now, in the next 8 minutes, I would try to walk you guys through gradient buffers and things like that from your homework one Autograd. And I would also first of all try to tell you how much of things you would have, right? It's similar to this lab over here. So what's going on in this lab, right? We use the node class, right, where each value is a node in a computational graph. In the homework, you would use operation class, where you would keep a bunch of operations, right? Because here we use a very simple example uh, in your actual Autograd engine, you would want to have addition, matmul, a bunch of activations, all of them put in one list that you can trigger using the global backward function, as we did over here, right? So you might want to go visit the lab again, look at how we implemented specifically the backward function and how the Autograd engine works, the entire pipeline. And once you have like the conceptual understanding of, oh, I'm not supposed to break the computational graph at any point in time, and then you can build on top of that. Does that make sense? Right. Okay. Everyone on Zoom, if that makes sense, or if you have any question, please let us know. Okay, I don't see any hands, anything. Then I would move to the Autograd engine. All right. So, what are we gonna do for homework one, part one Autograd? We build the Autograd engine, right, with a bunch of operations like add operations, all the backward method. We'll also have the backward function. By this backward method, I mean the global backward engine, as we talked about in this in today's lab, and then you'd have backward function associated with each node for addition, subtraction, multiplication, exponent, and then you would also build a bunch of modules like the linear module, the module for the loss function, for the activation functions, everything. So, like I said, you would have an operation class, right, where you would have a set of inputs, a list of input, what your output are. You'd have you'd also keep track of what gradients you'd want to update and what backward operation you want to trigger, right? So let's try to explain that with a simple example. Let's just think about this one operation that we have, right? H equals x matrix multiplied by w, right? So what are we gonna do? Our inputs are x and w, right? Our output is h. The updates that we would want to do is like, oh, we have the thing called gradient buffer, right? Which I'll get back to in next couple of minutes. But the first thing that you see here is for internal tracking of the gradient buffer. What we do is keep track of gradients of non-parameters, right? what are the parameters for our model, the weights, the biases, or anything that we want, right? What are not the parameters, these intermediate values, right? H or even Y, right? It's not something that we tune while training. So we have a separate buffer for tracking the gradients of these non-parametric values. And we also want to keep track of the gradient associated with our parameters, right? So in this case, the parameter is W, non-parametric variable is X. Then we're just gonna call the mathmol backward function the same way we did, so that our global backward can trigger this when we use it with all of these operations from this list, right? So this is how we instantiate any operation for your Autograd homework, right? So let's have a closer look at gradient buffer class, right? So you would want to store the gradient for intermediate values, as I said, right? Whose gradient we need, but they are not parameters of our model, right? For instance, X or H, right? Even Y in the example that we are considering. So we're just going to store this in a big buffer, right? So we need to have some memory allocated for it, right? So I want to focus on three important functions in this class: the add spot, the update the, parameter, and then the get parameter. So what you're going to do is you if you call add spot to X, right, to your numpy array, then what it would do is it would allocate the memory on this specific address, right, with a bunch of zeros would say par X. And we'd want to have this space so that we can keep so that when we instantiate operations like this, we can internally track the gradients. Then we would want to update our parameter, right? We again do it with plus equal to, and what it does is like it would go to that particular memory address and then add the gradient for that particular parameter. And if we want to get the gradient, right, that we stored by performing update param throughout our forward pass, then we just call get param, right? Now, so how does our entire Autograd engine looks like, right? So you have your gradient buffer, right, and then you have your list of operations, and then you would define your forward and backward global forward and backward function for this class, and then which would trigger the backward function associated with each node in your backpass. So you're supposed to okay, we don't have a lot of time, but oh yeah, that's pretty much it that I wanted to cover within this time span that we had. But yeah, one more thing: the global backward that I said that would be inside the Autograd. It would it would get the gradient of the output, right? It would get the first operation in its first iteration, and then it would call the backward function. That would trigger the backward method that you have defined for that specific node, and then it would just update the gradients, right? The parametric gradients and the non-parametric gradients. Remember that this is different from the way we updated the gradients in the gradient buffer, because here we want to update the gradients for your parameters, which are like weights and biases, right? That we didn't do before. We still have it for the gradient buffer as well. Yeah, that's pretty much it for today's lecture. I think we're on time, and if you guys have any question, please let me know. Yeah, and thank you everyone on the Zoom as well for joining. reach out to us if you have any question, or feel free to ask question. I'll stay here for a bit. Nice. If you guys have a question, shoot it. If not, you're free to go.
Okay, thank you, Kushi, Malia, and Anurag. Great job.
Thank you, Mia.
Thank you, Mia.
Thank you, Mia.